Hello everyone, welcome back. Today we're going to start talking about a new topic, rotational inertia, and its quintessential variable, moment of inertia, which is why the title here is different than the title of the video. Now, before we get any farther into our topics like rotational inertia and rotational kinetic energy, we definitely need to talk about this because it is an extremely important variable. And it is so important, I'm going to start with a conceptual idea of what moment of inertia is first. And to do that, I'm going to use this door. So this is an above view of a door that, let's say, was your bedroom door. So this is the hinge. This is the most part of the door, like I said, an above view, and it swings open like this. So every day you get up and you have to open this door, and it swings open this way. Now we're going to say the door is light. It's so light it's considered to be massless, which means opening this door is very easy. However, I'm going to add something. Let's say I take a really dense material, so it has a lot of mass, and I attach it to the door. So every time you open the door, the mass swings out this way and is here. And every time you open, you have to swing it this way, this way, this way, this way, this way, this way, back and forth. Now, this would make the door a little more difficult to open, but probably not by too much. Since we said the door itself is massless, opening the door on its own is really easy. However, I attach this mass to it, and now you have to move this mass a certain distance back and forth whenever you want to open or close the door, and the door just got a little more difficult to open. Now let's do a comparison, because I now am going to put up a second door. So the door on the right here is the same door. Again, massless, so it's very easy to open. However, I'm going to take another very dense mass here, and I'm going to stick it on the door. This time I'm going to stick it all the way at the end. So now this time, in order to open this door 90 degrees, you now have to take this mass and move it this whole distance so it ends up about here. So same door, same mass, just in two different places stuck to the door. My next question is going to be key to what we're talking about. If you had to open this door every single day multiple times, ignoring everything else, which of these two doors would be more difficult to open? Which one would give you more trouble to open every single time you had to open this door? The one on the left or the one on the right? 3, 2, 1. Well, if you answered the one on the right, you would be correct. Let's talk about why. Because remember, the mass of the doors is identical. The door itself is massless, and this is the same mass on both doors. It is just stuck to the door in a different place. So let's discuss why this door is so much more difficult to open. And to do that, we're going to start with these three translation equations I brought up earlier, from linear to rotational. For starters, the most obvious one here is the first one. If this is the hinge and this is the mass, let's say this distance is r. It's my radius. Because again, we are rotating the door when we quote unquote open it. Well, if that's r, that would mean this distance would then be 4r, because it's 4 times the radius. And my equation right here, arc length equals angular displacement times radius, means that if I have 4 times the radius, I have 4 times the arc length. So if you have this really massive object and you put it at the end of the door, you have to move it a larger distance every single day to rotate this door 90 degrees, where in the first situation, you only have to move it this far. And I'm going to quickly take this one step further in order to prove my point. If you open this door the same angular displacement, 90 degrees or pi over 2, in the same period of time, you will reach the same final angular velocity, which means you will have the same angular acceleration. So if you open this door the same angle, 90 degrees or pi over 2 in the same period of time, everything in the rotational column will be identical every single day. Now, if the mass is at 4 times the radius here, that means all of the linear variables are 4 times greater, which means your final velocity will be 4 times greater on the right than on the left. And if your change in velocity is 4 times greater, your change in momentum is 4 times greater. If we put up Newton's second law and your linear acceleration is 4 times greater, that means your force required is 4 times greater. Also, if your velocity is 4 times greater and we bring up the kinetic energy equation, Well, if V is 4 times greater, that means your kinetic energy is 16 times greater because V is squared. So, long story short, the door on the right is more difficult to open than the door on the left. You would need to provide more momentum, more force, and more kinetic energy, even though they have the same mass. Okay, now let's start talking about the details. All right, to get into more detail, we're going to simplify the situation. Instead of a door, we are just going to have this. And all this is a mass attached to a string, which is tied to an axis. And again, we are going to exert a force on the mass, and we are going to rotate the system 90 degrees. So the mass follows this path, basically. Now, if we have an axis and we are exerting a force that is perpendicular to the string, we have a force that is perpendicular to the lever arm. That also means that we have a radius. So when the block is here, I'm pushing upward, and when the block is here, I'm pushing to the left. In other words, the force and the string are always perpendicular to each other. I am also accelerating the mass. The initial velocity is 0. The final velocity is something larger than 0. So I have an acceleration. Since it's moving in a circular path, that also means I have an angular acceleration. And since we have a force, mass, and acceleration, let's bring up Newton's second law again. Net force equals mass times acceleration. Now, we have a perpendicular force and a radius, which means if I multiply r on both sides, and this is force perpendicular, that means on the left side I have a torque. And the right side, I now have mass, radius, and acceleration. Next up, if this is a linear acceleration, because the acceleration is always tangent to the circular path, I can do a substitution. I could substitute this acceleration with this, alpha times r, or angular acceleration times radius. On the left side, I'll keep torque the same, but on the right side, I now have this, mass times radius times alpha times radius. And if I simplify this, I have torque equals mass r squared times alpha. Now for the really important part. If torque is the rotational equivalent of force, and alpha, angular acceleration, is the rotational equivalent of angular acceleration, that means what I have left must be the angular equivalent of mass, and that happens to be mr squared. This is why, going back to my conceptual example with the door, if you put the mass farther away from the hinge, the door is more difficult to open, because it's not just the mass that matters, it's the radius that matters as well. In fact, that radius is so important, it is squared. And this property, this mass and radius square combination, is what is known as the moment of inertia for a point mass, which I'll get into in a minute. But again, it's not just the mass that matters. It is the distance from the axis that also matters. For rotational, this is considered a single variable that we're about to get into. So get out your notebook because it is definition time. Now, if you were to look up this definition on the internet or in the dictionary, it would tell you some weird definition about how difficult it is to rotate something and the inertia of it and blah, 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 blah. I'm going to simplify that by a great deal. Here's what you need to know. Moment of inertia, the rotational equivalent of mass. That's it. We have been working on our linear to rotational table, which we're going to get back to soon. And if you remember from this table, all the linear variables have their rotational equivalent: displacement, angular displacement, velocity, angular velocity, acceleration, angular acceleration. For now, this is exactly how I want you to think of moment of inertia. It is literally the rotational equivalent of mass. Wherever you see mass in a linear equation, you will put moment of inertia in the linear version of that equation. To get into a little more detail, the moment of inertia of an object is not just about the mass, but how far away from the axis the mass is located. The further from the axis, the larger the moment of inertia. Just like opening the door in that first example. The symbol is a capital I. The unit is kilograms meters squared. We can actually prove that with the relationship we just found. This is mass, units are kilograms, SI unit for radius is meters, and that is squared. And moment of inertia does not have a special nickname unit, so it's just kilograms times meters squared. All right, there are two more things I would like to talk about before the end for the day. The first deals with the fact that the equation we just derived is for a very specific shape. This is a point mass that is moving around in a circular path. It is very specific. But there is more than just a shape in the universe, obviously. In fact, there's a near infinite number of shapes in the universe. Let's take, for example, a baseball bat. If I took a baseball bat and started swinging it around, the mass is not just at one location relative to the axis. In fact, the mass is distributed without, and it's not even an even distribution. So the moment of inertia of a bat will be very different than the moment of inertia of a point mass. Now, the good news is you don't have to know the near infinite number of shapes in the universe. You really only need to know 4 of them. So let's talk about them. First, let's do the one we've already derived, the point mass. This means you have an object that is moving around in a circular path around a center axis of rotation, like a person on a merry-go-round or a planet orbiting its star. We've already derived this one, so I'm just going to put the equation. Moment of inertia of a point mass is mr squared. Now, the second shape you need to know is the ring. This is a ring just like you would wear on your finger. Now, imagine you take this ring and you roll it along the floor. If you do that, your center of axis of rotation is dead center of the ring. And importantly, all the mass on the ring is at this outer radius. And that's true for every part of the ring. Now, what's interesting is since all the mass is at that outer radius point, the moment of inertia for a ring is actually the same as the moment of inertia for a point mass because all that mass is still at the outer radius for both of them, which is nice considering since they are the same, remembering them should be a little easier. Now, things get a little different when we get to the disk or cylinder. This is the side view of the cylinder. This is basically a hockey puck or soup can, just from a side view. Now, the big difference between the disk and the ring is that for the ring, all the mass is at the outward edge. But for the disk or cylinder, the mass is distributed everywhere from the axis of rotation to the outer edge. In other words, everything you see in blue here is the same thickness. Now remember, as mass goes toward the axis of rotation, or a smaller radius, the moment of inertia gets smaller. That is why the moment of inertia for a disk is 1/2 mr squared. Now imagine if I took this disk that was made of clay, and I started crushing it in my hand to try to get as much of that mass toward the center axis as possible. Well, if we did that, we would then have a sphere. Again, imagine rolling the sphere across the floor, and the sphere is solid, kind of like a bowling ball or an orange. What separates this from the disk is the fact that if I did a cut through of the sphere here, just like an orange, I would have a lot of mass here. But from a side view of this orange rolling across the floor, if I took this slice, there's very little here. It's literally like me just slicing off the peel of the orange at the edge. So as it rolls, there is very little mass at the outer edge, but there is a lot more mass toward the center, unlike the disk that has a uniform distribution. And since there is a lot more mass at the center, that would mean that the moment of inertia of a sphere would be less than the moment of inertia of a disk. Disk is 1/2. A sphere is 2/5. 1/2 of 5 would be 2.5. So this is a little bit lower than that. Now, like I said earlier, there's an infinite number of shapes in the universe, so there's pretty much an infinite number of moments of inertia, but these are the 4 shapes you will be dealing with in a first-time physics course. You probably don't have to memorize these. They're usually given to you. That being said, I highly recommend you do so because there's only 4 of them, technically 3 of them because these 2 are the same. For any weird shape, the moment of inertia will be given to you, but these 4 you should know. Just a quick note, notice going from a ring to cylinder, the moment of inertia is literally cut in half, but going to the cylinder to sphere, it doesn't reduce by that much. All right, to really get that point across, there's one more thing I would like to show you. Here I have a ring, puck, and sphere, and I also have this ramp. What we're going to do is line up the ring, puck, and sphere at the top of this ramp, and then let them go. 3, 2, 1. All right, I'm going to pause it here, and there's something I want you to notice. The sphere beats the disk, but not by much. However, they both beat the ring by a good margin. This is directly related to their moments of inertia. These objects need to rotate in order to roll down the ramp. And the higher the moment of inertia, the more difficult it is to rotate. The moment of inertia for the sphere was 2/5 mr squared or 4/10 mr squared. The moment of inertia for the disk was 1/2 mr squared or 5/10 mr squared, larger than the sphere, but not by much. The ring was 1 mr squared or 10/10 mr squared, obviously the largest moment of inertia, therefore it is the most difficult to rotate and ends up in last place. Alright, I think this video is long enough. Make sure that you write these down. Then, have a good day. This is Mr. M signing off.